Hi folks, welcome to 9.4, which is a section on something called mathematical induction. So mathematical induction is a type of proof that you learn about in a little bit in pre-calc like we're doing right now, but really you'll use it again when you take some of those higher level math courses like linear algebra or discrete mathematics. You use mathematical induction quite a bit there. And so the idea behind mathematical induction is that we can say that if we can show that something is true for the first term, okay, and this is called the basis step, then we also want to show that it can be true for some term down the road, okay, in the sequence of numbers. And if we can show that, then basically it's like a domino effect. If the first one is true, and we can show that it's true for k plus 1 or some other term plus 1, then it's going to be true for every single thing in between, okay? So instead of showing it's true for every single case, we pick the basis step, and then we show the inductive step. And if both of those are true, then we've proved that the entire statement is true, okay? So a little bit more of a summary is that we're going to start by showing that p sub 1 is true. And again, this is our basis. And then we're going to assume that it's true for some random p sub k and prove that it's true for p sub k plus 1, or the next term. Okay, so think about it like we've got our p sub 1, and we show that that's true. And then instead of showing like p sub 2 and p sub 3, we kind of like skip a few and we pick like a random one, p sub k. And we assume that this one is true. And then we show that p sub k plus 1 is true. That means that everything in between and onward are always going to be true. Okay? So that's sort of the concept that we're using here. Now we're going to use this concept with some algebra to help us prove these different things. All right, so let's take a look at question number 1. We're going to use mathematical induction to prove that the sum of every positive integer n is n times n plus 1 over 2. Okay, so it turns out if you want to sit and add every single positive integer, you can figure out how many you want to add, and then there's a formula that tells you what that number is going to be. Okay, so we're going to start with our basis step. And so when you do mathematical induction, proof by mathematical induction, you need to start with this basis step. And so we're going to show that this is true for k equals 1, or the first term, okay? So that means the first positive integer is 1, okay? And so that should equal if we plug in 1 into this formula. So 1 times 1 plus 1 over 2. All right, nothing to simplify on the left-hand side, but that equals 1 times 2 over 2, or 1 equals 1. And so we have shown that our basis step is true, or that it's true for p sub 1. Now we're going to take a look at the inductive step. So remember, the inductive step is where we sort of skip a few, and we're going to assume that p sub k is true, and then we're going to show that the next term is true. Okay? So we assume that 1 plus 2 plus 3 plus ... all the way to k, some term k, is going to equal k times k plus 1 over 2. So we're going to assume that this is true. And now we're going to prove that it's true for if we have this. 1 plus 2 plus 3 plus ... plus k plus 1, because we're going to go an extra one. And now equals, well, that means everywhere I see a k, I'm going to need to plug in k plus 1. So k plus 1 times k plus 1 over 2. And so this k, all right, so this k became a k plus 1 because I wanted to find it for p of k plus 1. And then this k became this k plus 1. Okay, so I'm just plugging k plus 1 into the formula. All right, so this looks kind of messy, but we can do a substitution that makes it simplified pretty quickly. So what we might notice is that 1 plus 2 plus 3 all the way to k, another way to write that is k times k plus 1 over 2. That means that 1 plus 2 plus 3 plus all the way to k, I can replace with k times k plus 1 over 2. So let's do that. K times k plus 1 over 2. Okay, so that's the thing in the orange, plus that k plus 1 equals, and let me simplify some things on the other side. So k plus 1, and then k plus 1 is k plus 2 over 2. Okay, so my job now is to show that this left-hand side equals the right-hand side. So I look at this left-hand side and I notice that there's sort of two fractions, right? K times k plus 1 over 2, and then k plus 1 is really over 1. So I'm going to make a common denominator here. So k times k plus 1 over 2 plus, if I want k plus 1 to have a denominator of 2, I better multiply the top by 2 as well, so I don't change that. And we want to show that that's equal to k plus 1 times k plus 2 over 2. All right, so let's go ahead and combine these two fractions, but at the same time, I'm going to distribute this k to here and this 2 to here. And that's going to give me k squared plus k plus 2k plus 1 over 2 equals k plus 1 times k plus 2 over 2. And I think one last step should do it. This top, this k plus 2k gives me 3k. And then I can factor that to be k plus 1 times k plus 2 over 2 equals what I wanted it to equal. Okay? And so that's it. We've shown that it's true for the basis step. Okay? So again, the basis step was this one, that is true for k equals 1. And then we assume that if it's true for k, we want to show that it's true for k plus 1. And so we did some substitutions, we found a common denominator, and we were able to show at the end that those two are in fact true. That means that we have achieved our goal of using mathematical induction to prove that the sum of every positive integer n is n times n plus 1 over 2. Okay? So we're going to do 2 more examples. So I think that'll be 2 separate videos. You can see these questions are a little bit long, but let's see how that goes. But a lot of this is about substituting, being really solid with your algebra, and then really understanding this concept that it's all really just kind of like a row of dominoes. Okay, so if one is true, and then another one down the road is true, and the next one is true, that means everything in between and beyond is true. All right? See you back here for part 2.